Okay, so good morning, everyone. I'm Iwatsuki from Tokyo Institute of Technology, Japan. It's my great honor to attend this opening ceremony of the 25th International Conference on Mechatronics Technology, ICMT 2022, as one of honorable co-chairs. So I would like to offer my sincerest congratulations and thanks to all of you, especially to General Co-Chairs, Professors Yu, Liu, Huang, and Chong, and organizing committee members for hosting this hybrid conference with their great effort. So it's also our great pleasure to be here to continue this conference with great history while overcoming COVID-19. So I remember that this conference started as Trans-Pacific Workshop on Mechatronics Technology, which was held in Santa Clara, United States in 1996. That workshop focused on human resource development for mechatronics technology. I made my presentation on mechatronics education there. So 2 years later, the organizing committee in Taiwan determined to develop this workshop into an international conference and held ICMT 1998 in Hsinchu, Taiwan. So since then, a different country has hosted this ICMT every year. So I have also contributed to host this ICMT in Japan 4 times as one of local organizing committee members. So today, we can attend this 25th conference at here, Kaohsiung, Taiwan, and share a quite great history of which we should be proud. So I wish that all of you will enjoy presentations and discussions on the advanced mechatronics technologies in this ICMT 2022, and that ICMT will continue forever. Thank you very much.
Hello? Yeah, sorry. Sorry, Professor Liu, I think the network is not very clear. Yeah, it's not continuous. Yeah, I can hear you now. Yes, I can hear you now. Can I start presenting now, Professor Liu? Yeah. Is it okay for you to present my slides? Okay, thank you. Yeah, thank you. Thank you, Professor Liu. Thank you, audience. But are you allow me to share my screen? Because at the moment, I'm not able to share my slides. Okay, yeah, it works now. Okay, just give me a sec. I'm trying to share my screen. Okay, is everyone can see my screen? Yeah, everyone can see my screen. Okay, thank you. Thank you very much for Professor Liu for your key introduction, and also it's my great honor to be the keynote speaker in this introduction ceremony. So I think, okay, before I start my presentation, maybe I will, as a general co-chair, I would like to really appreciate and thanks for our partner, National Kaohsiung University Science and Technology, our honorable co-chair, Professor Iwasuki, and our general chair, Q-Wei Yu. Without the effort from everyone, it's impossible for us to run this conference. I think it's tremendous effort have been spent to make this happen. Especially we are in the post-COVID condition, and all emergency change in the last minute really make this difficult to happen. But thanks for all the colleagues there helping to make this. Okay, so welcome everyone to this ICMT 2022. And then I'm Dr. JJ Chong from Newcastle University. So today I'm going to share with you some of my work and the recent development in my lab regarding the smart lighting and the decentralized IoT edge devices for urban farming. So this will be the agenda for today. First, I give a quick introduction regarding what Newcastle University is doing, especially in my lab. Yep. Hold on, I'm sharing the full screen. Okay, give me a sec. Okay, hold on. Okay. How about now? Entire screen, okay? I'm sharing the entire. So I should share the entire screen. How about now? Is it what now? No. I see. Okay, I know what happened. Maybe I show in my first screen. Okay. Maybe I show screen. Is it okay now? All right. Thank you. Okay, sorry for the technical issue. Yeah, so just to repeat, today I'm going to share with you the topics, smart lighting and decentralized IoT edge devices for urban farming. Okay, so the agenda for today is I will give you a quick introduction about Newcastle University, some of our excellence centers, and also the purpose of doing this urban farming and try to transit into the edge computing infrastructure. And then some problem statement that identified by Singapore government and some of our collaborator. Why do we need to focus on this urban farming technology? And also I'm showing you the proposed solution that we developed in our lab, some result, preliminary result, and this work is still continuous, and then the future work, all right? Then of course, after the session, then there's a Q&A, everyone can ask, and if you need seek for the collaboration, of course, we are more than happy to collaborate with anyone in the room. So introduction is, I'm not sure everyone here familiar or been to Newcastle in UK. So our main campus, is located northeast in the UK, Newcastle University, as shown in the point here. Okay, so let me just maybe bring out my pointer. So we are always constantly ranked as the top 150 university in the world. And then here, there are some highlights for us to advertise the excellency of Newcastle University. So first, Newcastle University is one of the largest engineering group in the UK for over 140 years. It's a very traditional and old university. And then we are internationally leading in research field. And this one, we cost about £50 million for us to build the National Innovative Center for Data. And then we also have the UK National Institute Smart Data Innovation. If you see the direction and the money that's spent in Newcastle University, we are actually moving into digitalization and energy. So here we also have our UK's National Center for Energy System Integration, Advanced Propulsion Center. This is what we work quite closely with the previous co-chair, the Professor Trung. He will be the keynote speaker tomorrow. Then we also have a collaboration center with Dyson. And also, lastly, we are serving the largest MSc program in the UK. So this is all our main campus in UK. And in Singapore itself, because for me, I'm located in Singapore from time to time also, especially for the summer, we also go back to our main campus for deliver some networking event and also some program exchange. In Singapore itself, Newcastle's University in Singapore, we have been here for about 15 years. So if you see this figure here, in Singapore, we are actually serve two purposes and two programs. One is working collaborative with the local university, Singapore Institution of Technology, to deliver 4 main undergraduate programs here, which is included electrical power, marine, chemical and mechanical design and manufacturing. This is where I'm serving here. In parallel, we also have another research center that we call it as Newcastle Research and Innovation Institute. In here, we do all our research, postgraduate teaching, and also, of course, PhD consultation. And then this is where I'm serving as energy and sustainability. So if you look at the distribution of our network, our work, and our collaboration, basically we are bridging the network in Singapore and also our colleague in UK to try to maximize the effort of Singapore University in Singapore, Newcastle University in Singapore. So, come back to our speech today. First, why do we need to spend the effort on developing indoor farming? First is Singapore is very different to many countries because in Singapore, there are 90% of the domestic food we are rely on import. Right? Because of this, and especially this issue been highlighted after the pandemic, is the risk of distribution due to any policy change in the food exporting country. We experienced this just in this year when Malaysia suddenly issued a new policy saying that they are not able to export the chicken to Singapore. So the price of the chicken is immediately spiked for several percent. Then any climate change, there's a potential issue. Pandemic is what we're facing it now. When there's a pandemic, suddenly we are running out of the local supply. And possibly, if there's a war happen, we are not able to always dependence on all the import to supply the food in Singapore. So because of this, the Singapore government's food agency released a new policy, what we call it as 30 by 30. By 2030, we aim to develop the capability and capacity of our agriculture and agri-food industry to produce 30% of Singapore nutrition need. So we want to have self-supply to our local market. What we want to do is we want to grow the food locally. So with this aim, we are aiming to produce 30% of local production food. Okay, within this percentage, 20% coming from vegetable and fruit, and 10% coming from the seafood, like the protein. So from this end, to achieve this, of course, we need to work collaboratively with different agencies, different local companies, by leverage the technology to grow more with less. That's the reason, because Singapore is a small country, we don't have a lot of land. So with this certain amount of with this limitation, how can we maximize the growth? So we need to leverage the technology by first. Second, we need to develop a pipeline of local agri talent. Okay, so after we integrate the talent, the technology, how can we develop the associated pipeline to train the local in order for them to familiarize with this technology, in order for them to quickly take on to the technology and then grow the skill. We need to encourage the customer, okay, the consumer, to choose the local supply food, which I think this worked quite successfully in after the pandemic, and with the local brand. And then leverage technology to farm sustainability. Last, unlock more space. Especially, as I said just now, we have no space. So how can we maximize our current space? On the rooftop, on a car park, this is where we are now targeted to work closely with different agencies to maximize this effort. So we know the objective already set, some guidance already prepared, but the question is still there. If we want to develop by our own under this small area and then leverage the high technology to maximize this growth, what is the cost? Okay, what is the cost? From the research, we know, of course, if you want to develop this, we have to rely on indoor farming. All right. For indoor farming, from the research, we know the price is 10 times more than the traditional farming. If you want to produce the equivalent amount of biomass. Secondly, electrical consumption. For the indoor farming compared to the traditional farming, there are tremendously amount of energy have to be spent compared to the traditional farming. So estimatedly, okay, when we go through this research, we know roughly if you want to develop the small indoor farming to cater the need in Singapore, roughly we need to spend about 3,500 kilowatt hour per square meter. All right. So if you don't know how to quantify or how to visualize this energy spend, roughly we are able to understand this amount of energy we are able to power 4-room flat for a year. And if you want to charge your Tesla, you're able to charge 350 times and serve you more than 200,026 kilometers. So you know tremendous amount of energy will be spent in order for us to bring indoor farming to build the local need to meet 30% of the reason behind is because using the artificial sunlight, again, of course, I bring down to several issues. Using the artificial sunlight, they are about 60% to 80% of the consumption because large amount of the luminaires actually poor use. We have the luminaire system, we have the lighting system, but not all the light is actually transmitted to the growth of our plant. Second, once we build a smart or intelligent lighting system, the next one is how do we ensure if we distribute this technology out, how do we ensure our food safety, they are actually fulfilling the food safety and security compliance. Right? So we need to ensure not only improving the lighting system, we also need to trace and also monitoring real time with all the growth. And then lastly is because we want to leverage the technology. Let's say we develop a prototype, we introduce the technology to the local company, but how can we scale up this technology? And especially we are emphasizing on low cost and scalable. So we need to target that on IoT devices. So this is the 3 areas that our group currently working on to help this Singapore to act fulfilling this aim. So come back to this question. We know lighting system, we want to improve. I mean, the first aim is we want to improve the lighting system. But the question to us is how much do we need? How much do we need to feed our plant? Right? The intensity. A human is very straightforward. If you feed a lot of junk food to a human, then you will grow fat, right? It's the same for our plant. So we know the low light intensity, meaning to say, how do we optimize? When we look into the problem, we want to know, okay, lighting system we can optimize by investigate the biological growth. But as the mechanical engineers or as a mechatronic approach, how can we ensure this plant here is always able to receive the right amount of lighting and without wasting it? So meaning to say the light cannot be placed too close to the plant. First, we don't want to place the light too close to the plant, and also we want to ensure there's an optimized height for different plant and for different growth. Then when we go to the industry, when we go work with the partners, here, these are the partners that they are currently working in Singapore. They are also supplied to the local grow. This company, the Artisan Green, they are the horizontal farming. This is the vertical farming, Artisan and Sutener. They also grow a lot of indoor farm. All the lighting system currently, they are fixed. The height is fixed. So they are not optimizing the height, even though we are going through several stages of the biological growth. So from the vegetation to vegetation, they are all under different lighting needed, right? So they are not optimizing this. So always currently at a fixed mounting height, the light is actually waste. They are felt on an empty space between the plant and various growth cycle stage. So our proposed solution here is we are looking at to develop a dynamic mounting height, which allow us to adjust the lighting system autonomously. I mean, our ultimate goal depend on different plant, different growing cycle. We are able to optimize this height and then maximize the efficiency between the lighting system to the plant need. So here allow us to maximize the light intensity and reduce the stray light distribution. Secondly, we want to maximize the light intensity, moving a set of luminous across the row of the plant in the grow area at a set of time interval. So we are not only want to fix on a certain height, we also want to dynamically moving along the grow area. By doing this, we allow the number of luminous to be reduced while providing the adequate light and good airflow. So the whole system becomes dynamic. Lastly, as we want to ensure this can be scalable and safe following the compliance, we want the whole grow tank is able to give us the real-time monitoring and then implement the IoT sensor. We want to understand the farmers, the local farmer, what nutrition that they are using, what recipe that they're using to grow, and then we want to trace every single process from the seed, when they plant the seed, until the final grow, until the final plant to the market. So from here, this will allow us to trace real-time data, tracking, monitoring, and control the height optimization. And then there are some important measurement. I mean, from biological to the real implementation. First one, we're looking at the PAR, which is the photosynthesis active range. By all the plant that we investigate, the range is between 400 nm to 700 nm for the spectrum for the photosynthesis. We have the photosynthetic proton flux density, which is PBFD. This is to reflect the measure the light that actually arrive at the crops canopy in the RA region. Then we also have the daylight intensity, the integrate. So here is a measure by PPFD divided by the light received by the plant per day, because this is the one that we use to measure our light. We are using the sensor to measure this reading. Okay, so ultimately we want to build this cubicle grow tent and then scale it out to the local farming. So before we scale it out, we need to test it. So we build a prototype. So this prototype is a Cartesian robot light moving system as shown in the picture. And here allow us to move on the vertical axis and on the horizontal axis. And then let's say this is a grow area. Of course, this can be scaled about, as I say. And then on the right-hand side is all the sensors, all the controllers and the sensor that we are using. And later on, I will introduce you step by step why we are using this sensor, because as I say, we are aiming for low cost and we are aiming to scale this to different agency and to different corporator. So we want this one to be implemented on the flat, in the car park or on the rooftop. So for the sensor that we are using, first one, we need to have the ultrasound sensor to ensure we have a right amount of distance from the plant canopy height to our lighting system. Second, multiple lighting system are under investigation. So we have different multiple lighting for different plant needs. And then here, because we are aiming for low cost lighting sensor, the lux sensor. So we need to do a calibration by comparing this, the apogee. This one is quite expensive, roughly about 1,000 pounds, the sensor. This one is only less than 100 pounds sensor. So we want this to do the pre-calibration first to ensure our reading is able to provide the accuracy, provide a good accuracy. So we do this comparison, and then we are able to do the key factor conversion. So by doing this, we are able to know, okay, even though we use a low-cost lux sensor, it's still able to give us a good, accurate reading for the light intensity and also the converting PPFD to the daylight intensity, daylight integrate. Then this is the full IoT architecture. Okay, so in this full IoT architecture, on the left hand side is all from we have our prototype, our sensor, and then here is we allow the sensor to communicate with the local microcontroller, which method with the Wi-Fi capability. And then here we need to talk about how do we decentralize our IoT system, which is on the right hand side. If you look into this Docker system, okay, this Docker architecture actually allow us to scale out this IoT solution in a very simplest way and using a very low power consumption for fueling the computation functioning. Okay, it doesn't need to have a huge computation power and also doesn't consume a lot of power, electric power consumption for our microcontroller. So this Docker system is built on the Raspberry Pi. Within the Docker system, this as the main server, we have different apps actually download to this Docker that allow us to do different integration and then data communication. And I'll explain you later in the coming slides. But the other thing we want to highlight is because from this server, the local network here, the Wi-Fi, we know the internet provider, sometimes they provide us the dynamic domain for our IP. So here, in order for us to for our user to have a user-friendly, they don't need to always configure their IP. We have this dynamics DNS, the dark DNS we call. They are able to detect the change of our IP, then it automatically update the IP accordingly. So the user, anytime the IP is updated, then they are able to prompt it and also adjust it itself. So from this this proposed architecture, we are not only able to fulfilling to scale up this technology, and also we are able to extend any sensor that we need. So for example, if you want to implement a new sensor, yes, we can plug it into this architecture and then develop it and scale up to our collaborator. Okay, so the reason here is why we want to use this scalable communication by using Node-RED and MQTT protocol, which is very easy. I will show you. This is very easy. Here, our MQTT broker, the protocol using the Qt, and then our Node-RED serve as a client. So for our sensor, as long as we have this communication under publish and subscribe, and under this flow, then we are able to do the message communication. So for example, if I want to adjust the height, okay, the platform, our lighting platform, as long as I'm subscribed to this platform, okay, then my MQTT communication protocol is able to send this message to my broker. Then it receives from our client side. So which is very simple, and this logical flow is able to spin off easily and then allow the new farmer or allow anyone who are not familiar with programming quickly pick up this this infrastructure and this knowledge. Okay, this is all for the MQTT message out. Then we also have the MQTT message in, the flowchart. So for example, from a client to the broker. So here, again, our Raspberry Pi here, the local computer processor, have the MQTT broker here. So whatever PPFD reading that we read from our client is able to publish. So this sensor reading is able to publish through our broker and then publish to our client, okay, which is our user. And then from this user, we are not only showing the reading on the interface, user interface, but we are at the same time, in the real time, we also publish to the influx database. Then later, we can also pull this data out for visualization. Okay, very simple architecture. Under the node connection, this is described as, so let's say we have a sensor here, client side, we go to the broker, then we are able to depend on where you want to send this message to, who is your subscriber, then we just attach this to the need of our customer. Okay, so as I said just now, the whole thing is not only able to do the control by one direction, it's bi-direction, but we also provide a very good data query and user interface. It receives the data, store in the database, and then later you can serve this as the user interface. Okay, as I show here, From the front end, the user is able to control through their local network or their devices to control the platform. Okay, this is using manually, to monitoring the lighting, what lighting they're using, the setting, to monitoring the power use. Okay, of course, this functionality can be expanded. As I say, all the sensor can be easily plugged in following our IoT infrastructure network. Then it can be used for serving any other purposes. If you want to monitoring the flow rate of the water, you can also do that. So here we are able to do the visualization under the Grafana interface. So we know okay, what is the PPFD reading across the day, the current, the power, and then of course under this filtering system, we are able to see the data under different time period. Okay, we also able to do the real time camera system to our plant, our grow area. Okay, so from this architecture, from this network, we are able to see the real time monitoring and then able to do the bidirectional control from the user to our infrastructure or to our device, edge device. Then after we set out this device, the next thing is for us to, there are two hypotheses. First one, we understand potential energy saving. Is it really save a lot of energy when we have this smart system and the new IoT solution? So we want to test the plant can grow well, and then the light required for the plant can fulfilling even the case that the light intensity is fluctuated, right? Because we are dynamically moving up and down and left and right. So the lighting now is changed. We want to ensure the plant still can grow well and then saving the energy. Secondly, a lot of questions asking, okay, you are doing a dynamic system. There are a lot of energy will be spent on your motor, on your microcontroller, on your IoT things, right? How can this be compared to the traditional farming, the fixed lighting system? So the second hypothesis that we want to test is the motor actually contribute the consumption, right? And the controller. We want to understand what is the energy consumption. If you take into account the overall spend from the microcontroller, lighting system, and the entire system. So first one, we test the plant growth. We take the plant growth and the morphology test. So to validate the hypothesis one, the plant will grow equally and given a dynamic moving lighting. So how do we do that? First one is, I will explain the table on the right hand side later. So we set different height, and then we record all the daylight integral, the reading, and then we document it up. So if you see every single time, every single sequence, or even every single matrix, we try to take the reading. Okay, and then we place our sensor always at the bottom. Then we set different position, set different height position. So vertical position and horizontal position. So from here, we have the equation for us to calculate what happens if the motor is moving, the system is actually moving. Then how can we convert this into the dynamic reading? Okay, static reading is very easy. DLI, the daylight integral is very easy. We are only using this equation for us to calculate. But if we convert to the dynamic, then how can we quantify this reading? So by doing this experiment, we are able to come up a list of table or a list of criteria for us to understand under what combination, under what height, or under what PPFD, what is the suggested daylight integral for us to use. So if you look at the highlighted section, there are multiple combinations here. For example, if I want to achieve this reading here, there can be multiple experiment set or multiple lighting condition allow us to do that. You can either do 15 hours, 16 hours, or you can either lowering down your platform. Okay, so we developed this metric for us to optimize our morphology growth. So we can see from the height, the luminance, and the PPFD relationship, we know, okay, when we test out different height, okay, when we test different height, the lighting height from 5 cm to 30 cm away from our plant, we know the distribution of the plant actually is quite equal, but only if the lighting system is very close to the plant, okay, the intensity is increasing. You can see there's a spike here, which is when the lighting system is 5 cm away from the plant. Okay, it's a repeated graph, but I just compare it from 5 cm to 30 cm. So there's a huge difference here, okay, the equal distribution of the load intensity. The reason is because, I mean, we investigate it. The reason is because there are large amount of intermeshing lighting beam from individual LED sheet, okay? Because when the lighting system is very close to the plant, actually the intermeshing between the light. So you have different lighting overlapping. So this is what we can observe it or we can prove it from this chart here, okay? So you see, when the lighting system is far away from the plant, there's a high intensity located in the center. Okay, so this one is more distributed out. Then if we plot this into the 3D contour, then we are able to understand, okay, so under different height, different lighting, and different position, this data here, okay, this data here, we are able to visualize it in the 3D map. So this is, from here, we are able to know, okay, there's a uniform total the length of the light bar as this light is more intensive directly and not allowed to form the distribution beam. Obviously, we don't want to form this distribution beam because it's only a local area getting the benefit of this light, and maybe it's too strong for the plant. And we want to distribute this one more equally to the whole entire growth surface or to the canopy height of the canopy surface. Then we are not only investigate the lighting, we're not only investigating the lighting intensity from the sensor, we also really do the biological growth, okay? From this, we are doing the pak choy, okay? In Chinese, we call this pak choy. Actually, it's a quite popular vegetables dish in Singapore market. So we compare the biological behaviors, the morphological tests. So we know, okay, it's not significantly improved. If you see, we actually grow 20 plant within our grow area. Then we weight it, we weight the final plant. Then there's no significant difference. This one under the dynamics setup, this is about 280 grams, sum up everything. And then this is about 290 grams. So there's not big advantages compared to for the biological growth, which is we are expected because we are not changing the writing the recipe, right? We are still equally distributed the light throughout the whole growing area. So this is what we expected. So second hypothesis, which is the thing that we are interested to know, is we want to know, are we actually using more energy or are we actually saving more energy? Okay, so the whole power, this is the sensor that we are using. We have the plug sensor because we want to allow a user-friendly deployment. So we want our customer is able to plug in this easily. So we actually suggest this energy monitors plug system for them to plug into their existing infrastructure. And we set different conditions. We have the motor driver sleeping mode and under the normal mode. So as long as the motor is not operating, we want the motor to turn into the sleeping mode. And then we compare the whole energy consumption within 30 days of the morphological test. So from here, we have a big data set just now, right? Here I just actually highlighted. So if I compare the static one, okay, a static 4 lighting system, and the dynamics here are only using 2 lighting system. So from here, we actually, under this comparison, one set of experiment comparison, we are actually saving this amount of energy. We're actually saving this amount of energy. Okay, less energy is used. So from here, we are able to save about 100,000 of cost if you want to produce 100 tons of vegetable. Okay, for one grow tank, maybe it's not a lot, but if you scale out this into the entire Singapore use, then there's a significant amount of energy can be saved from this proposed solution. Here, if you see, we also take into account the energy use, the depreciation of the motor, and the microcontroller. Okay, here we also compare. I think the slide is slightly order slightly changed, but here we can see the power consumption saving under always on the stepper motor under this condition and under the sleeping mode. So we are able to save quite a lot of power. So we also compare the lighting system, the luminous system under static, 1 lighting, 2 lighting, 4 lighting, and also under the dynamic. For dynamic, because under the daylight integrate, the parameters, we know at least we need to have 2 luminates. We need to have 2 lighting systems. One is not enough to equally distribute across the grow area. So from here, we measure power usage. Then we know actually there's a big, about 20% of energy saving compared to these two. Okay. Of course, if you compare to static 1 and 2, it's not comparable because static 1, the one luminaire is not able to supply the entire lighting system for the whole growing area. And 2 luminaires also is not able to optimize the growth. So the plant at the age is not able to grow healthily. So this is the equivalent comparison when we compare static 4 lighting system to 2 lighting system. So at least we know they are 20% of energy saving. Okay. So this comes to the end. Of course, this is just the preliminary work. We still have a lot of data need to test, a lot of experimenting to go through, because you can see the data set there. There's multiple combinations. What happens if you only test more powerful lighting system, but cut down the photosynthesis time, like to 4 hours to 6 hours. So we also want to investigate how much energy will be used. So our future work, because we want to develop the whole ecosystem for serving the Singapore food need. So this whole ecosystem, we also need to integrate the robotic pick and place system to operate the harvesting and seeding. Okay, we are not only provide the lighting system, we also want to integrate or incorporate this robot pick and place system. Now we are actually using 6 models to drive. So now moving forward, we want to reduce this. We want to reduce this motor. When we scale the entire thing out, we want to reduce the motor that can be used and simplify the system. And then, of course, as I said just now, we want to go through more tests, more parameter tests for us to do the energy study. Here, we also integrate the neural network. We want to learn using machine learning to understand when we have different data, when we have different plant, what is the best optimized lighting system can be used to support the biological growth. And then there's another thing that we work with another institute. We want to study the computation, the dynamic, the airflow, the system airflow within our entire dynamic system, because normally we want to place our lighting system as close to the plant as possible, but we also want to investigate what is the heat, what is the localized heat that could be generated if this plant is actually placed too close, if the light is placed too close to the plant, and what happens if this having the dynamic feature, will this heat be carried out? So this is something that we want to investigate. And lastly, we also want to emphasize on the cybersecurity. This is what we want to move the entire IoT protocol into Web3. Okay, so this is the future direction that our research group is actually targeting now. Last, I will show you a demonstration of this lighting system. Just a short demonstration. So it allows us to move up and down, and front and back, left and right. Okay, thank you very much. Any question? Sorry, Professor Leo, it's not very clear. I can't hear. You mean the weight the weight of the vegetable or the weight of the entire device? Yeah. Okay. Yeah. Maybe I show. Yeah. So yeah, if you see this slide, actually the weight of our biomass, the plant actually the static one has the more heavier biological weight compared to the dynamic one. Uh, it's only 10 gram different. We have about 20 veggie 20 plant here. In total, it's only 10 gram different. But of course, we want to investigate more. We want to do grow more. We want to investigate different plant. But at the moment, we should expect that there's not much difference between static and dynamic regarding the biological growth because we didn't change the lighting recipe. We keep the same recipe. We keep the same light integral. So it shouldn't have much change, but as what we expected is we should keep a safe energy. Thank you. I'm using MQTT protocol. Yeah. How much time? The MQTT protocol that I'm using now, the package is a Mosquito, is open source. So the reason we are targeting for open source because we are a lot of, as I said, we want to scale out this technology, and we are working with a lot of local companies, which they don't have a big budget, and then we want them to also learn the process of how to implement it. So, for example, if we show them the full technology, the full IoT solution, later on they are able to have built out this knowledge and allow them to implement it themselves. So that's why we use the open source MQTT Mosquito protocol. Sorry, Professor Liu, can you say again? You mean the control strategy? Uh, you sorry, I can't hear you very clear, but you say how much time different? Oh, you mean the lagging time? Almost is under real time condition. There's no lagging. So whenever time you key in the message or the command to move the platform, is actually to respond immediately. At the moment, it's manually at the moment, but ultimately, after we integrate the whole machine learning method in or the AI in, then we want to have the optimized growing feature. Thank you. thank you, Professor Liu. Thank you, the audience.